Hey, how's it going? Welcome back to another streaming session. I want to take a look at some of the things that like the reading coach, and so different people use this reading coach a little differently, which was really cool to see. That's really what I was interested in, was seeing like how do you interact with the AI? How does it actually help you explore the reading material? How does it give you credit for actually interacting with the readings and thinking about these kind of topics? So it did exactly what it was supposed to do. It was just to give you some kind of sounding board and kind of explore some topics that way. So I wanted to look at that, and then also I know today we're working on the first project. So projects are meant to be a little bit more open-ended than the homeworks. Homeworks are usually like kind of like, hey, do this task. This first project is kind of like doing a task, like doing some stuff, but we're also trying to, like, there's some open-endedness of like show that it converges to an analytical solution. There's more than one way to do that. And we'll see if the learning coach can actually figure that out for us. And then what else? And yeah, what is the final temperature as T goes to infinity? This one, like if you're doing the math of the equation, then you can kind of figure it out, like plug in T, take the limit as T goes to infinity, E goes to 0, so now it's TA. But if we want to say that the Euler integration goes to the same temperature, then we need some evidence that Euler and this equation are the same answer. So I want to take a look at that, and also kind of so let's pop open this reading coach. As it takes a second, we'll say open. So in the reading quiz, I thought this was kind of cool. A few people had like asked something and they use this to say like, I'm stuck. So it asked you about the print statement, and neat part was like, it would give you an example of like, oh look, hey, let's break it down. The print statement does this, here's the output. So and then it would move on, give you another question. And how would I use this? I would use the print statement to show the two numbers added. And then let's see what the learning coach says. Cool. So there's that, which was, and yeah, and even as this comes up, like what's variable types and assignments, I could say, like, skip it. And then it would give me more questions, and yeah. So that was pretty cool. I thought that was a neat way of using this learning coach of like, hey, either I don't understand it and then I could get more information about it, or skip it and just move on to another question in either way. So some people ended up with 8 or 9 questions in their learning coach kind of assessment. Other people were kind of 3 or 4 or 5 questions. And again, the main thing is just thinking about the readings. So you can always pop open our website. Well, if you go, we'll go here, right? Go Husky CT is always like a good starting point, because there's always so here's the playlist, the course tour, and then the course syllabus. So if you're trying to figure out like, all right, well, how do I use the print function? I could go to this interacting with Python, and the first thing is like the very first program is this print statement. or if it's asking about like what are these special variables, I could go inside it like, all right, well that's still interacting with Python. And let's go down to why Python, let's get started. Reflection maybe. There we go. Variables and their types, maybe somewhere in here. Strings, errors, types, more assignments. Now here's some Boolean variables. True, false, and here, right in there, special variables. And then not implemented is one that it didn't really ask us about. But that would be, this is a good way of this learning coach like kind of quiz that it's giving you. I'm not taking, I'm never going to take the assessment of your interactions with it at face value, but it's a nice kind of litmus. It's a nice test for yourself of like, can I get an A on this? But the main thing is like that you do it and share the results here. All right, so let's try this since I'm working on project 01 and I need to, let's see what project 1 tells us to do. Maybe we should copy in all of the, well, you know what, let's do this. Come in here. This is a little kind of like AI hack. Like, since we have access to Markdown like this, we can copy the actual Markdown code. And that's gonna be better than trying to go through the website and just like copy in this stuff, because it'll copy in these formulas, but they're not going to be formatted correctly. But meanwhile, if I go right into here, all the formulas are in what's called LaTeX. So this is a markdown cell with LaTeX equations. All these are just kind of like different ways that we've figured out, like, how do we get complicated math and science concepts into websites? Markdown and LaTeX equations work pretty well. So let's try this. Let's I need to answer this first question. So let's see what our learning coach tells us to do. Here's Newton's law of cooling. All right, so it's giving us, it's restating the problem and then calculating out this derivative. So using a finite difference derivative and then plugging in to that equation to find K. So let's see how it worked, right? Copy this code and we'll come into my getting started project. And the first question is, does it actually plug in the numbers that I wanted it to plug in? So it's giving me 85 degrees is my initial, giving me my final at 80, and then 65 is my ambient temperature, okay? And I think I've seen code formatted like this, so I think people have tried like copying and pasting this result before. So Learning Coach is kind of giving us a good direction to start in. And I kind of like how it's breaking it down into both the derivative and the solution for this K term. So what this is doing is saying that this left-hand side is a value, and that value is based on the change in temperature over a change in time. So delta T over delta time, delta temp over delta time is equal to this whole thing, negative K times current temperature minus ambient temperature. All right, so that's what I want. It seems like it's working correctly. Let's give it a shot. And then here in this case, 45 minutes, it's not telling me, well, it does say time interval in hours, which is good that it's actually specifying what the units are. Sometimes it doesn't do that. And even here, it's not specifying, really, I want to say temperature in Fahrenheit. In Fahrenheit. Yeah, so that's one thing that it's kind of missing here, is that the units are sometimes involved, sometimes they're not, but you really need to make sure, especially if you're using AI for this kind of thing, really double check these units. So if everything is in hours, this time constant is going to be in 1 over hours. That's the units that I'm dealing with here. And the reason that one works, this, whenever I have a derivative, this is a temperature per time, so Fahrenheit per hour equals K times Fahrenheit, delta Fahrenheit. So K has to be a 1 over hour. So if I'm calculating changes in temperature over hours, then my K term is going to have units of 1 over hours. And that's something, this one, that was a question that came up in our GitHub discussions earlier today too. If we come in, there was a question about, like, should we convert everything into SI units? And it's like, yeah, you can. You can use any consistent set of units you want, because the actual math and code that you're doing, it doesn't really care whether you use SI or if you want to use Celsius and hours and like horsepower or something. But for the most part, we're just dealing with temperatures and times. So as long as you're consistent and you keep track of your units, you can use it however you want. You could even look at days if you wanted, like take this of like how many degrees per day is this dropping. Kind of a weird number to deal with, because now you add like that factor of 24 to the thing, but it's not the end of the world. So it seems like it's working pretty well, and then it prints out this this value, which is kind of cool that it worked out this way. So here's something that a lot of people aren't sure about. When I calculate this K, should I use a T initial or should I use a T final? Because it gives me two different answers. Here's T final. For T sub T in T lowercase final. So it gives us, so I'm just taking either the initial or the final temperature and saying whether it's 0.333 or 0.444 time constant. And yeah, I don't really like that. The time constant K is. And now let's take a look to figure out which one we're supposed to be using. The derivative that we calculated was T of T plus delta T minus T of T over delta T. This is called a forward difference method. So let's draw out what's happening here. At 11 a.m. and 11:40. 4:45 a.m. I know the temperature was 85 Fahrenheit, and then it dropped down to 80 Fahrenheit. There's only one slope that I can calculate. Like, if I'm using a finite difference method, this slope is always going to be 5 degrees over 45 minutes. However I want to calculate that, like either 5 over 3/4 or 5 over 45, but it's always the same number. It's always the same slope. So then the question is that slope true for this point? Like, do I need a new slope over here when I get to, like, is this point 0 and this is point 1? Or is this point 0 and this is point 1? If that question kind of makes sense. Like, where is this slope, the true slope for that time? And some of you may be looking at this of like, well, the curve has a constant, the slope keeps changing, right? Like, it's not actually a constant slope for that whole 45 minutes. So what are you even talking about? And this is a truncation error that we're looking at, that we're approximating a continuous function as a straight line function. So I can either say this is time t, so the slope is t of t plus delta t minus t of current time t over delta t. And if that's the case, this is equal to, here, let's move this down a little bit. This is saying that it's 85 minus 80 over 45 minutes, which is equal to k times, now it's t of t, right? So 80 minus 65. Or I could just as easily say that this is t of t minus t of t minus delta t, like that, all over delta t. And it doesn't change this result, right? It's still 85 minus 80 over 45 minutes, but now k is multiplied by t of t, which is the 85 minus that 65. So here, again, this is our forward difference, this is our backward difference. We're going to come back to derivatives and talking about forward and backward difference. We'll even look at another one called a central difference method, which is, some of you might have thought about that, even just looking at these two answers of like, well, if these two answers are correct, couldn't I take the average of them? And that's basically what a central difference method would be, where we would take these two numbers and then the real result is somewhere in between them, because they're both wrong for kind of different, the same reason but in opposite directions, if that makes sense. So there is error because we're taking a continuous function, turning it into a discrete line, but it's not too bad. We'll get an answer. But yeah, so here we could say for, oh yeah, I guess I want to say forward and backward difference, but like that. Yeah, I'm just documenting which one is which. So 1/3 for a forward method, a little bit more than that, 0.44 for a backwards difference method. Cool. Hopefully this helps. Again, another use of AI, but if you're using AI, you really got to go through and check like what is this doing and how, because right now I just took code. I mean, I had written this, so technically I was taking my own ideas and giving it to them. But if you're taking someone else's question and plugging it into an AI bot, saying like, hey, just give me an answer, go through, check all these results. Like, is this was the temperature given in Fahrenheit? Is this still Fahrenheit? Like, are all of these things the right units? It's very bad with units. It's okay at setting up equations, but very bad at tracking units. So be careful, especially with that, especially as engineers. Okay, cool. Thanks a lot.